All right, 9-7, day 1. We are going to dive into the final topic of Chapter 9, which is probability. Really, for the most part, if we look at our learning objective here, we'll focus on the probability of a single event. Day 2, we'll get into the mutually exclusive, independent, and complements. Okay? But today I really want to focus on some of the fundamental stuff of probability because it can be a topic that some really struggle with. And sometimes I worry that really when you get down to like the most basic stuff, that might be where we're missing some connections on what's going on. So let's start down here with some definitions. We kind of modify the definition of an experiment, okay? Some other contexts might say that, for our definition, that's a simulation, okay? But we're saying that experiment is just a process in which the outcome is unknown. Outcomes are any possible result. Okay, a sample space, and that's what we're going to start with, is generating sample spaces, is a list of all the possible outcomes. And an event is the outcome we're looking for. You're going to see event and sample space come up, because when I was referring to some of that really fundamental stuff of probability, that's kind of what I was getting at, is there's a relationship between those two that's a huge part of probability, okay? All right, so notation-wise, you'll see this a little bit, that if I flip one coin, sample spaces are thought of as sets, and we usually use squiggly brackets to denote a set. So S is just short for sample space. Really, really small sample space. Heads, tails. The only two outcomes that you could have if you're flipping a single coin. Okay? Remember, sample space for your experiment. This would be a really simple experiment, by the way, that you're just flipping one or two coins. A sample space is a list of all the possible outcomes that you could get. If you do two of them, you could get heads on both. Heads on the first, tails on the second. Tails on the first, heads on the second. And yes, we do have to think about both of those as separate outcomes. Okay? And tails, tails. All right, it doesn't take all that long before generating a sample space can kind of get out of control. We'll be pretty limited in how many that we will do, just largely because we'll have sample spaces that could involve 4.5 million outcomes. That's not one where we're going to list them, okay? You can, I'm going to go up to 3 coins, and this one's going to be a little bit trickier. You probably could go through and just try to think of all the possibilities and list them off. You could do that. There's 8 of them total, so it might be a little bit harder to get all of them. You could also use what's called a tree diagram. Each set of what we call branches represents one flip. We need 3. Okay? Now here's how a tree diagram works. You always start right here And you can follow what we call a path through the diagram. Here would be flip 1, flip 2, and flip 3. That outcome would be heads on all 3 flips. How about heads on the first, heads on the second, tails on the third? How about heads on the first, tails on the second, heads on the third? You can follow each one of those paths, and you can kind of work your way down through the diagram. You certainly don't need to sketch over the path. That's not necessary. But I'll finish them off here with heads, tails, tails. Tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. Okay? Again, that's using a tree diagram to generate a sample space that's by no means huge, but again, it doesn't take a really big sample space before just kind of listing all the outcomes off without some kind of method can get a little bit tricky. All right, so here's the big thing with a sample space and an event. It's where the definition of probability comes from. Okay, when you're talking about the likelihood that event occurs, you need 2 numbers. Okay, your event, again, that's the one that you're measuring. You need to know how many ways can that event occur. That's the number that goes on top of the fraction. N sub s is the number of outcomes in the sample space. That goes on the bottom. Okay? This is specifically what I was referring to for those that really tend to struggle with probability. I feel like it's this concept right here that they might be missing. All right? This is where probabilities come from. It's where they always come from. Okay? Now, the n could be 0 if you have no, if it's an outcome that is impossible and can't occur. The number on the bottom of the fraction has all the outcomes, so at the biggest, the number of events could be the same as the sample space. That's guaranteed the event will occur. That's the big implication for what that means, is probabilities have to be between 0 and 1. Okay? So now, the next few I'm going to get into aren't going to be super complicated, but I want to make sure we're coming back to this definition. For example, we already generated the sample space for flipping 2 coins. What's the probability that both land heads up? Well, on top, I put a 1, because when we listed out all the outcomes, we saw that there's only one way that can happen. You have to flip the first coin and get heads, and then you need to flip the second one and get heads. We listed out that sample space for 2 coins. There were 4. It would be a 1 out of 4 or a 0.25 chance that would happen. All right, here's another one that's just the probability of a single event. Okay? Think of our definition now. 2 things. How many outcomes are in the sample space? How many ways can the event that we're referring to happen? So if you draw 1 card from a regular deck, there's 52 cards in the deck. There's your sample space. There's 52 different ones that you could get. How many are aces? You have to be a little bit familiar with playing cards to get that. There's 4. 4 out of 52, or if you went as a decimal, it would be a 0.0769. If you wanted to think about it as a percent, it's about 7.7% chance that you would get dealt an ace. Okay, so let's split this up into two parts. Number of ways the event can occur and the number of outcomes in the sample space. Let's do the sample space first. Notice I keep coming back to this definition. So what I'm looking for is n sub s. You're rolling two fair six-sided die. Really actually becomes a counting principle from 9.6, that we have two events and they both have 6 outcomes. So if we do 6 times 6, here's a case where I'm not interested in listing out all the elements of the sample space. I could do it if I wanted, but there's 36 of them, so not interested. But I do want that number for the bottom of my probability. Okay, when I roll 2 dice, there's 36 different outcomes that I could get. We want the sum of the 2 dice to be 7. So now what we need to look at is how many ways can that happen. Right? It's not all 36. If I got a 1 on my first die and a 6 on the second, that would work. 2 and a 5, 3 and a 4, 4 and 3, 5 and 2, 6 and 1. What about a 7 and a 0? Right? Those are impossible, as you know, in either one of those dice you can't get a 0 and you can't get a 7. By my count, there's 6 different ways that we could get a sum of a 7. So you could say 1/6 or 0.16 repeating. Okay. Again, if you want to think about it as a percent, it's like between 16 and 17%. So I don't want to spend a ton of time on this one. We could talk about it more in class if you wanted to. But I did want to mention that it, again, fits the definition of the probability of an event really well. Okay, and that's because of this. On any given outcome, we should have a 1/6 chance of rolling that number on a 6-sided die. Okay, a 12-sided has each number twice. So for every single number, it's still just the outcomes of 1 through 6. It's asking you to kind of go through and verify that, you know, it would not. You could use 2 12-sided die and it would work just the same as 2 6-sided, or even one of them. But now, if the outcomes of 1, 2, 3, 4, 5, and 6 can happen twice, it really gets back to this. The probability of rolling any one of those numbers, 1 through 6, doesn't change. It still sits at 0.16 repeating. This is the number of ways the event can occur, the number of events in the sample space. The numbers are different, but probability is all about the ratio of the two, and there it's the same. All right, there's a lot of different lottery games that you could play. Okay, this one's from Arizona. You choose 6 numbers between 1 to 41. Okay, you're going to buy 1 ticket. What are the odds you win? Okay. Here's what this is going to look like. We're buying 1 ticket, so n of E would be the number of ways that we could win. Unfortunately, there's only going to be 1, because we're only going to buy 1 ticket. The one and only way that we can win is the ticket that we buy has to match the 6 numbers that are selected. Okay, now the order doesn't matter. So what we need down at the bottom is how many different combinations of 6 numbers are possible if you're selecting those 6 numbers from 1 to 41. It's 41, choose 6. So we'll have 41 factorial over 35 factorial times 6 factorial. You can tell at this point the odds aren't going to be very high. So we have 41 times 40 times 39 times 38 times 37 times 36 times 35 factorial. Remember, I would have to keep going all the way down to 1, but I stop at 35 because those will cancel, and then we can multiply 41 down to 36. 6 factorial is about 720. The bottom would come out to be 4,496,388. Your odds would be 1 out of that because we only bought a single ticket. Okay. If we wanted to see this number as a decimal, it would be 0.000000222. Okay. It's probability, so it's between 0 and 1, but it's not very likely, so it's a little bit closer on the 0 side of things. All right, last one for today. Okay, again, coming back to the same definition. What's your event? How many ways can it occur? How many outcomes are in your sample space? Okay, we have this geographical breakdown of the U.S. as to how many colleges or universities are in those regions. If we randomly select one university, what are the odds that it comes from one of the 3 southern regions? Okay, so the very first thing I need is the total of all the universities in the country, regardless of which area they're from. Now, this problem's a little bit mean. It gives us all the numbers, but it doesn't give us the sum. So we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers that we have to add up. Luckily, I'll do it for you. 4,163. How many of those universities are from the South? Well, that would be those, and those. That is 1,370. Okay. So the event that I'm referring to is selecting one of those schools. That's the number of ways this event could occur. If I pick one of those 1,370 universities, the probability that I pick one of those is the ratio of those 2 numbers, which is about 0.329.